Good morning everyone, and welcome to lecture number 3 of maths optional. And in this lecture number 3 of maths optional, we are going to start from the topic trace of the matrix. Up to here we had already learnt in the previous classes that what is super lower triangular matrix, okay, and what are the notes which important remarks which we have to remember, okay. So these important remarks are of very much use in the examination. These two important remarks which I had already told you to learn in the last lecture, these are very much important remarks, okay. So we will start from the next topic, which is trace of a matrix, okay. Now trace of the matrix, as the name suggests, the name of the sum of all diagonal elements of a matrix is called trace of a matrix. Now what does it mean by diagonal elements? I had already told you in the last class that these elements, the elements which are present like this, these are called as diagonal elements. Now I had already told you that in order to determine the principal diagonal, diagonal means this is what? Principal diagonal basically, okay, principal diagonal. Now in order to determine the principal diagonal, we need to have one thing in mind, that these matrices must be square matrices, okay. If the matrices are not square matrices, then principal diagonal can't be determined. In order to have the principal diagonal determined, we must have a square matrix. Square matrix means what kind of matrix? Either it can be 2 cross 2, either it can be 3 cross 3, either it can be 4 cross 4, okay. Means m cross n matrix where m equal to n will be the condition, okay. In an m cross n matrix, m must be equal to n, then it will be a square matrix. And if it will be a square matrix, only then its principal diagonal can be determined. Otherwise, if the matrix is not a square matrix, its principal diagonal cannot be determined. And if it is not a square matrix, suppose it is a rectangular matrix, and in that rectangular matrix, suppose its principal diagonal was not determined, can't be determined, then obviously its trace will also be not defined, okay. So for the trace to be defined for a matrix, the matrix must be a square matrix. This is the important condition which we get from here, okay. So what will be the trace of this matrix? Clearly this red one is the principal diagonal. So trace of this matrix will be clearly trace A, which is equal to 1 plus 7, which is the sum of principal diagonal elements, and that will be equal to 8 in turn, okay. That will be in turn equal to 8. Now properties of trace of a matrix, okay. We have to learn the properties of trace of a matrix. Suppose if A and B be two square matrices, okay. Suppose A and B are two square matrices of same order. Same order means what? Suppose this is 2 cross 2, then this will also be 2 cross 2, okay. And it is given that square matrices. I had already told you that we are learning properties of trace of a matrix, and trace is determined only for square matrices. So clearly all these properties of trace of a matrix will be determined only for square matrices, right? So if A and B be two square matrices of the same order, suppose they are of the same order, that is, if this is 2 cross 2, that is also 2 cross 2. If this is 3 cross 3, then this one is also 3 cross 3, right? If this is 4 cross 4, then this one is also 4 cross 4, like that, okay. And suppose K is any scalar. What does it mean by scalar? Scalar simply means that it is a normal number, okay. Scalar simply means that it is a normal number. It is not a matrix. Scalar, what does it mean by scalar? Scalar means a normal multiplicative number, okay, which is not a matrix. So suppose K is any scalar, then what are the properties which we have? The properties are trace of A plus B will be equal to trace A plus trace B, okay. Then we have trace Ka equal to K times trace A, okay. The scalar K will come out of this trace. So let us understand the meaning of these first two properties. The meaning is very simple, that suppose I have a equal to 1 2 3 4, okay, and b equal to suppose 3 4 5 6. Suppose like this is the case, then what will happen? Suppose I find a plus b, okay, suppose I find a plus b and find its trace, okay. So what will be that? I will add a and b and find out the trace, okay. But I can equate it to this thing, this very thing, that I will find trace of a separately and I will find trace of b separately. Means over here like that this the trace is 5, in this case the trace is 9, and I will then add 5 and 9, okay. So clearly I will get, what is that, 14. So the trace of this, instead of finding the sum first and then taking the trace, I can add the individual traces and get the final result, right? So that is the thing. So trace of a plus b is equal to trace a plus trace b, okay. Means trace of two matrices added together, trace of two matrices added together is equal to the sum of the traces of individual matrices, okay. So sum of two matrices added together, trace of the sum of two matrices added together is equal to the sum of the traces of individual matrices. Got it? So this is the thing. Now the second property, we know that trace Ka is equal to K trace A. That is, K has come out of the trace, okay. K has clearly come out of the trace. That means that K is a scalar which has come out. Now always whenever a matrix, any matrix, suppose I have such a matrix that suppose A equal to 1 2 3 4, this is the matrix suppose, and suppose if there is some number multiplied to it, okay, suppose I multiply number 4a to it, suppose 4 is multiplied to it, then what will happen when I take the trace of this, okay, when I take the trace of 4a, then clearly I can write 4 times of trace a, okay. I can clearly write it like that, okay. And it is a common sense also, you can apply your common sense, that this 4 when it will go inside, it will be multiplied by this also and this also, okay, and after it is multiplied by that or that and that, then clearly it is a very very common sense kind of thing, okay. So you have to, you can write it on the paper and think yourself that how it is common sense, okay. You will realize that it is really a common sense only, okay. Now trace K1A, you can clearly see over here in the third equation, trace K1A plus K2B, right? Then K1 and K2 will come out, okay. K1 and K2 will come out again by this property only, okay. And this third property is nothing but the combination of these two first and second properties. What is this third property? It is clearly a combination of first and second properties, okay. So K1 will come out, then K1 trace A plus K2 will come out, K2 trace B, okay. So I don't think there is any need to further explain this, okay. Now this fourth property says that trace of A transpose, okay. Trace of A transpose is equal to trace of A transpose A, which is equal to this much, okay. Now this is very interesting, we have not learned trace yet, right? We haven't learned trace yet, not trace, transpose yet, okay. Trace we have learned, we have not learned transpose, okay. So what does it mean by transpose? Let us see in the next slide, and then we should come back to this slide, okay. So we will go to the next slide and see, okay. So transpose of a matrix. Now what is this transpose of a matrix? Transpose of a matrix can be obtained by interchanging row and column of a matrix. Okay, clearly it is written that transpose of a matrix can be obtained by interchanging row and column of a matrix. If a given matrix is A, then we interchange row and column of the matrix A. It is denoted by A prime or A to the power small t or A to the power. We should not read it A to the power, but we can call it suffix. Okay, so A prime or A t, A small t or A capital T. All these are read as A transpose. Okay. So how to find out the transpose of a matrix? What does it mean by transpose? So you can see it clearly over here, that suppose we have 2 cross 3 matrix called as A. We have this 2 cross 3 matrix which is A, and we have to find out its transpose. Then what will we do? This A11, this is what? This is A11, this is what? A12, this is what? A13, right? This is what? A21, this is what? A22, this is what? A23, right? Then clearly I will arrange this one, okay, this one in the vertical form, this one in the vertical form I will arrange, and then side by side this will also be arranged in the vertical form like this. Okay, so eventually I will get the transpose like this. Okay, so you have to do nothing but convert the row. 1 2 3 was the row, 1 2 3 was the row, first row. So 1 2 3 will be the first column in the transpose. Okay, 1 2 3 was the first row in the original matrix. In the original matrix, 1 2 3 was the first row. So in the transpose matrix, 1 2 3 will be the first column. Similarly, if 2 5 7 is the second row in the original matrix, then 2 5 7 will be the second column in the transpose. Okay, 2 5 7 will be the second column in transpose, and 1 2 3 was the first row in the original matrix, so 1 2 3 will be the first column in the transpose. Okay, so in this way you can understand this thing. And instead of it being called as 2 cross 3, then it will be called as 3 cross 2, because over here it is 3, over here it is 2, and in this case over here it is 2, over here it is 3. So the order will be interchanged. Instead of m cross n, it will be n cross m then. Okay, instead of m cross n, it will be n cross m. Order will be changed, right? So such is the case. And over here there is one important property which says that for transpose of a matrix, the matrix is not necessarily a square matrix. You have to remember this thing very well. Okay, over the past years I have realized that students get confused in this, that they get confused between the trace and transpose. Okay, I had already told you that trace is defined only for a square matrix. I had already told you that trace is only defined for a square matrix. Why trace is defined only for a square matrix? Because principal diagonal will be defined only for a square matrix. As principal diagonal is defined only for a square matrix, so clearly trace will also be defined only for a square matrix, right? But the case of transpose is very different. Even if it is a rectangular matrix, okay, it is not necessary, or read the words carefully, not necessarily means it can be square matrix or it can't be, it may be or it may not be. Okay, this matrix may be a square matrix. If a matrix is a square matrix, then also its transpose can be found out, and if the matrix is not a square matrix, then also its transpose can be found out. Okay, so both kind of matrices are possible for a transpose to be found out. If it is a square matrix, then also its transpose can be found out, and if it is not a square matrix, even then its transpose can be found out. Okay, so transpose has no conditions whatsoever with regard to it being a square matrix. Okay, so it has no restriction. Transpose has no restriction. But when it comes to trace will be defined only for a square matrix. Okay, so you have to remember this thing very well. For transpose of a matrix, the matrix is not necessarily a square matrix. Just remember this thing. Now we will go to the previous slide and see the last property which we had not studied. Okay, trace A transpose. Now you got the meaning of transpose. Okay, so suppose this A is 2 cross 2, then transpose will also be 2 cross 2 only. Okay, so clearly if we find out the transpose, suppose I have A equal to 1 2 3 4, then what will be its transpose? Clearly its transpose will be 1 2 3 4, right? Such will be its transpose, right? And when we multiply A and A transpose, when we multiplied these two, and when we multiply A transpose and A, the product comes out to be commutative in this case, in this particular case. Okay, so when we try to find out the trace of these, then clearly instead of multiplying the whole matrice, matrices and then finding out whether what it comes out, okay, just simply take the sum of diagonal elements squared. Okay, so what will we do? What does it mean by this? ai square summation I equal to 1 to n. What does it mean? Clearly you can put the values 1 1 2 etc. So a11 square plus a22 square. And what are these a11 and a22? These are principal diagonal elements. Okay, and clearly you can see this thing that 1 4 and 1 4. So the principal diagonal elements in transpose as well as original matrices are the same. Principal diagonal elements are going to be the same. So clearly you can square them, means 1 square plus 4 square is the case. Okay, 1 square plus 4 square over here, so it is 17. Okay, so your calculation is reduced. Instead of finding the multiplication of A with A transpose and then taking its trace, I will directly square the diagonal elements and add them. Okay, I am going to obtain the same result. You need not go into the proof of all this. Okay, you can go into the proof also, no problem, but as far as our syllabus is concerned, so I don't think its proof will ever be asked. Okay, I don't think so that its proof will be asked. Sometimes if they are very that kind of person, the examiner is very he is very angry, then he can give the proof of this also, but proving this is not a big task. Okay, you know, proving this is not at all a big task. Why it is not a big task? You can clearly take any matrices. You can take any matrices a11 a12 a13 like that, of n cross n order. Okay, just take it, then take its transpose. Okay, and term by term just multiply and you will obtain the result. So the proof is also not a big task. It is 12th standard proof. Okay, 12th standard level proof. So it is a very easy kind of proof. Okay, so hopefully you will be able to do this. Okay, the proof of that I mean. Okay, so the transpose of a matrix, the matrix is not necessarily a square matrix. This also we have learnt. Okay, so that it is not a necessarily a square matrix. Very good. Now properties of transpose of a matrix. We will look at the transpose properties of transpose. What are the various properties of the transpose of a matrix? Now if suppose A and B be two square matrices of the same order, suppose that A and B are two square matrices of the same order and K be any scalar, the way we had learned the properties of trace, similarly we are learning the properties of transpose now. Okay, so clearly if A and B are two, now why it has been taken that they are square matrices? Okay, the question arises that you had already told us that in order to find the transpose of a matrix, okay, you had told us that for finding the transpose of a matrix, the matrix is not necessarily a square matrix. Then while writing the properties of transpose of a matrix, when you are writing the properties of transpose of a matrix, okay, why are you telling that they are square matrices? Why are you taking that condition? Someone may ask that. So let me be very clear with you that if A and B are two square matrices of same order, these properties which we are learning, the properties of transpose which we are learning right now, those are applicable only if A and B are square matrices. If A and B are rectangular matrices, then these properties of transpose of matrix will not be applicable. Remember one thing very well, that in order to find the transpose of a matrix, the matrix need not be a square matrix. Okay, for finding the transpose as given here, this was a rectangular matrix, still I was able to find out its transpose. But when I want to use the properties of transpose, when I want to use these properties which are given below, which are the properties of transpose, in order to use them, I must have A and B as two square matrices. Only then these properties will be applicable. Otherwise these properties will not be applicable. Okay, so although the transpose can be found out for a rectangular matrix too, but the properties will be applicable only in case of square matrices. And in case of trace, the trace was defined only for square matrix. Okay, so there is a difference between the two. जो ट्रेस था हमारा, ट्रेस क्या था? ट्रेस हमारा केवल और केवल स्क्वायर मैट्रिक्स के लिए अप्लीकेबल चीज़ थी, ठीक है ना. लेकिन ट्रांसपोज जो है रेक्टेंगुलर मैट्रिक्स का भी फाइंड आउट किया जा सकता है, ठीक है ना. लेकिन बात ऐसी है कि जब प्रॉपर्टी फाइंड आउट करते हैं ट्रांसपोज की, जब ये प्रॉपर्टीज़ लिखी जाती है जो नीचे लिखी गई है, तो ये प्रॉपर्टीज़ तभी अप्लीकेबल होगी जब जो ट्रांसपोज ले रहे हो जिस मैट्रिक्स का वो स्क्वायर मैट्रिक्स है, तभी ये नीचे दी हुई प्रॉपर्टीज़ जो है वो अप्लीकेबल होगी, ठीक है ना. अगर ए और बी जब स्क्वायर होंगे तभी, ठीक है ना. पर ट्रेस में क्या था? ट्रेस में ऐसा था कि अगर तुम्हारा मैट्रिक्स स्क्वायर नहीं है, स्क्वायर मैट्रिक्स नहीं है, तो वो ट्रेस ही डिफाइंड नहीं रहता था. तो यहाँ पे फ़र्क ये है कि यहाँ पे ट्रांसपोज तो डिफाइंड होगा, रेक्टेंगुलर मैट्रिक्स का भी डिफाइंड होगा ट्रांसपोज, लेकिन अगर हमको ये वाली प्रॉपर्टीज़ अप्लाई करनी है तो फिर से स्क्वायर मैट्रिक्स ही लगेगा. ये जितनी भी प्रॉपर्टीज़ लिखी हुई है ये रेक्टेंगुलर मैट्रिक्स के लिए अप्लीकेबल नहीं है. हालांकि ट्रांसपोज डिफाइंड होता है रेक्टेंगुलर मैट्रिक्स के लिए भी, फिर भी ये प्रॉपर्टीज़ रेक्टेंगुलर मैट्रिक्स के केस में अप्लीकेबल नहीं होगी. दिस इज़ व्हाट इज़ मीन्ड बाय दिस. ओके, so I told you in Hindi also somewhat, so that you can understand it better. Okay, so what are the properties of transpose of a matrix? Let A and B be two square matrices of same order, K be any scalar. Okay, K is any scalar suppose, then what will happen? A plus B transpose when we try to take, okay, A plus B transpose when we try to take, when we add two matrices and take its transpose, then clearly we get what we get is A transpose plus B transpose. Okay, that is again a kind of distributivity kind of thing. Okay, so sum of two matrices when its transpose is taken. When two matrices are added and its transpose is taken, clearly it is equal to the transpose of individual matrices added together. Okay, transpose of individual matrices added together. Okay, so such is the case. Now over here also you can apply one common sense very well. What kind of common sense you can apply? That this addition of two matrices, it will be defined only if both have the same order. Okay, so that is the different case, but in this case both must be square matrices. Okay, that is a different matter, just ignore it. Okay, I was telling you something else, but let's not go into that right now, it will confuse you. Okay, so properties of transpose of a matrix: if A and B be two square matrices of same order, K be any scalar, then these are the four properties which you must remember in case of transpose. Okay, that is A plus B transpose is equal to A transpose plus B transpose. K A transpose is equal to K times of A transpose, that is the scalar K will come out. A B transpose is equal to B transpose A transpose, means we will invert this. Okay, when we take A B transpose, what will we do? The latter term will come first. Okay, and the first term will go later. Got it? First term will go afterwards and the latter term will come first one. It will become first one. Okay, and A transpose ka transpose. Okay, A transpose is transpose. When transpose of A transpose is taken, then we get the same thing. We get the original matrices. We get the original matrix. Okay, when transpose of A transpose is taken, we get the original matrix. Got it? So these are some of the properties. And similarly over here one more property will be there, that A B C transpose is there, suppose. Okay, then what will it be? C transpose B transpose A transpose. Okay, like that it will be, means this order will be reverted and transpose will be taken. Got it? So you must remember all these properties. Okay, these will be very much useful for you while solving the problems. And theoretical questions are also asked, but they are asked rarely. Okay, theoretical questions are asked rarely, those also I will cover. Okay, those also I will cover. Now let's see what all we are going to learn. Okay, what all we are going to learn in the upcoming lectures. The summary of that I am going to tell you now. Okay, so let's see. Yes friends, so we are going to see what all we are going to see in the upcoming lectures. That thing I am telling you right now. Okay, so we are going to see in the upcoming lectures the transpose of a matrix, conjugate of a matrix. Okay, then in transpose of a matrix we basically have symmetric matrix, skew symmetric matrix, orthogonal matrix consisting of real elements. Okay, conjugate of a matrix which has three types: Hermitian matrix, skew Hermitian matrix, unitary matrix. Okay, it has complex elements. Okay, so all these are the topics on which we are going to proceed in the upcoming classes basically. Okay, so and one recommendation I want to give you: on social media there is a lot of fight going on, there are lot of communal message being forwarded, so just don't pay any attention to social media. That's what I am saying. And do not get involved in texting. Okay, stay away from texting, I will say, because texting kills time. Okay, texting kills time. Texting and reels, Instagram reels, just ignore. No need to watch Instagram reels and texting. No need to do that. It is a mere waste of time, sheer waste of time. Okay. So symmetric matrix, a square matrix A equal to Aij, okay, is called symmetric matrix. Now when will it be called as symmetric? If A transpose will be equal to A, then it will be called as symmetric matrix. Okay. Now Aij equal to Aj for all I comma j. Okay. What does this mean? Simply, if you interchange the row number and column number, you simply get the identical element. Okay. Suppose I have a matrix like this. Okay. Clearly this is a square matrix. Okay. So Aij equal to Aj simply means that this element, the one which has been given over here, okay, this element will be equal to this element. Okay. This element will be equal to this element, and this element will be equal to this element. So elements on both the sides of principal diagonal, this is what? This is your principal diagonal. So elements on both the sides of this principal diagonal are identical, and Aij is equal to your Aj basically for all I comma j, for all I and j's. Okay. If you clearly take the transpose of this, then it will be clearly equal to A, as you can see over here. Clearly, if you take the transpose, that will come out to be equal to A. Okay. So square matrix A equal to Aij is called symmetric matrix. Okay. IFF means if and only if. If and only if A transpose is equal to A. Okay, that is Aij equal to Aj for all I comma j. Okay. Aij equal to Aj for all I comma j. So such a matrix will be called as symmetric matrix. You have to remember this thing properly. Okay. Now properties of symmetric matrix. Now symmetric matrix is such a square matrix in which elements on both the sides of this principal diagonal are equal. Okay. As you can look over here. So this element will be equal to this one, this will be equal to this one, and this will be equal to this one. If it is a 3 cross 3 matrix. Okay. If it is 4 cross 4, then also such a situation will arise. Okay. So what are the properties of symmetric matrix? In a symmetric matrix, all the elements above and below the principal diagonal, as told to you right now. Okay. All the elements above and below the principal diagonal, as you can see over here. Okay. Above this principal diagonal, above this principal diagonal and below this principal diagonal, elements are equal. Okay. And also all these elements A, B, C, H, G, F are real ones. Okay. All these are real ones. And clearly, if you try to take A transpose, then what will happen? This row, the horizontal one, okay, if you try to take the transpose, then what will happen? Clearly, when you try to take the transpose, one thing will be very sure, that AHJ, okay, this AHJ will be written like this, this HBF will be written like this GFC will be written like this. So ultimately you are going to obtain the same thing. Okay. You will get the same, you will get it to be same as A, that is your original matrix. A transpose will be equal to your A. Okay. So this is the thing. If A be any symmetric matrix, okay, if suppose A is any symmetric matrix, then Ka is also symmetric matrix. If we multiply any symmetric matrix A with K is any scalar. Okay. K is any scalar. So that Ka matrix is also symmetric matrix. This is a quite obvious statement, because when you write K outside a matrix, then K is simply multiplied by every element inside the matrix. What does it mean by K times matrix A? K times matrix A simply means that all the elements of matrix A will be multiplied by this K. Okay. And when you take its transpose, it will be clearly K times A, okay, as A transpose is equal to A, okay. So Ka is a symmetric matrix, okay. So let A be any symmetric matrix, then Ka is also symmetric matrix. So I had already told you that transpose of a symmetric matrix is equal to the same matrix. So if we try to take the transpose of Ka, then it should come out to be equal to Ka only, okay. I had already told you, right, that A transpose equal to A implies that A is symmetric. What does it imply? That A is symmetric, okay. So clearly, if I take instead of A, I take Ka suppose, and if I try to take its transpose, and if it comes out to be equal to Ka, then Ka will be symmetric. Instead of A, just put Ka over here everywhere. So it will turn out that Ka is symmetric. So let us find out from the properties of transpose whether it really comes out to be equal to Ka. So Ka transpose is equal to K times of A transpose, okay. All these two terms are different because over here there is a bracket. So bracket implies that K transpose will also be taken and A transpose will also be taken. Now K times of A transpose, it will be equivalent to that because K is a complete scalar quantity, okay. So K times of A transpose will come, and after that we know that very well that it is given in our problem that A is symmetric. So as A is symmetric, so A transpose will come out to be even again equal to A. You can put it like that, okay. So Ka transpose is equal to Ka, okay. So Ka is symmetric matrix. Got it? If A and B be two square matrices, okay. Suppose A and B are two square matrices of same order. A and B are two square matrices of same order. Square matrices, what does it mean by square matrices? It will be of the n cross n form. Its order will be of the form n cross n or m cross m also you can say, okay. So that will be a square matrix, which I have already told you that number of rows will be equal to the number of columns, okay. So A and B are two square matrices, they have the same order, means we can call that if this is 2 cross 2, then this will also be 2 cross 2. If A is 3 cross 3, if A is 3 cross 3, then B will also be 3 cross 3. If A is 4 cross 4, then B will also be 4 cross 4 only, okay. So such matrices are called symmetric matrices, okay. Not symmetric, same order matrices, okay. So these two square matrices are same order, then K1 and K2 are two scalars, then what will happen? K1A plus K2B, okay. K1A plus K2B, when I try to take its transpose, clearly K1A transpose plus K2B transpose. I had already told you in the in the beginning that how are the properties of transpose. So transpose follows the distributivity property. As it follows the distributivity property, so clearly this T will be distributed over here and over here. So on both of them transpose will be distributed. So it got distributed, and after that we know this very well that K1 and K2 are scalars, means normal numbers. So by the above property which I told you just before this, we can write K1A transpose, K2B transpose, okay. And A and B are symmetric also, it is given same order and they are symmetric also, okay. It is given in the question. In the question is right over here that A and B are symmetric also, okay. Symmetric also. I haven't written over here, but you should write it over there also. So A transpose will be equal to A and B transpose will come out to be B. So after that when A and B are your symmetric matrices, clearly K1A plus K2B means linear combination of the matrices will also be what? Linear combination of the matrices will also be your symmetric, okay. So K1A plus K2B is your linear combination of the matrices and it is also symmetric. That is if A and B, so I have written over here, if A and B be two symmetric matrices of same order, then their linear combination is also symmetric matrix. That is what has been written. Okay, so you must remember this property too. Just remember this property too. Okay, now in the fourth one, if A and B be two symmetric matrices, okay, suppose A and B are two symmetric matrices of same order. Again, the situation which was in the above property, the same situation is over here, that they are square matrix also and symmetric also. Okay, so as soon as I say that they are symmetric, they will be square matrix also. Okay, because symmetry is possible only in square matrix. This also you will have to remember. Okay, symmetry is only possible in square matrix, because what does it mean by symmetry? Symmetry means that both the elements above and below the principal diagonal are same, and elements, if above and below the principal diagonal elements are need to be same for a matrix to be symmetric, then clearly it must be a square matrix, because principal diagonal is decidable. Principal diagonal can be decided only for a square matrix, right? So that's why if I say that they are symmetric matrices, so it eventually implies that they must be square matrix also. Okay, so this is the property that AB plus BA is also a symmetric matrix. A and B are two symmetric matrices of same order, then AB plus BA is also symmetric matrix. This thing you will have to remember. Okay, so the proof of it is written over here. Okay, AB plus BA, whenever we have to prove that it is symmetric, in order to prove symmetry we have to take the transpose. So let's take the AB plus BA transpose. So by the property of distributivity, AB transpose plus BA transpose will be the case. Then again, the property which I had told you, that when two matrices are in multiplication, we have to just invert. Okay, so B transpose A transpose, A transpose B transpose. Okay, so it came out to be BA AB. Okay, then again I have changed the order. Just write this over here and write this over here. Okay, so what will you get? You will get AB plus BA eventually. You will get AB plus BA instead of BA plus AB. You will get AB plus BA. Okay, so you know this very well, that how did this from this step transition to this step, how did it happen? We know that A and B are symmetric matrices, so these two conditions will hold. So A transpose will be equal to A, B transpose will be equal to B, A transpose will be equal to A, B transpose will be equal to B. So that's how your equation looks like. Okay, so it will come out to be AB plus BA, hence AB plus BA is symmetric matrix. Okay, no need to further discuss this. Now if A be any square matrix, then A plus A transpose is symmetric matrix. Now this also you have to prove. Okay, how will you prove this? Over here there is no need to be no need to say that it is basically your symmetric. Okay, over here in this fifth condition, A be any square matrix, you need not say. Okay, no need to say symmetric over here. In fifth condition, no need to say it is symmetric. Okay, why? Because the proof will tell you. Proof will tell you A plus A transpose equal to A transpose. This will go here, this will also go here. Okay, so it went on both these terms. And A transpose transpose. So A transpose is A transpose, and A transpose is A. Your A transpose is A. So this term you will write over here, this term you will write over here. Okay, and afterwards you get A plus A transpose. So A plus A transpose, when we take its transpose, A plus A transpose, when we take its transpose, it has come out to be A plus A transpose. And whenever we take transpose, okay, just a second. Okay, just a second. Okay. So clearly A plus A transpose has come out to be A plus A transpose. So A plus A transpose is symmetric matrix clearly. Okay, you got this thing very well. Okay, so some issue was there at my end. Okay, the issue is resolved now. Now if A be any square matrix, then A transpose and A transpose A both are symmetric matrices. This is also quite obvious thing. A transpose transpose A transpose transpose A transpose. Okay, then again this. Okay, so it is a quite common sense thing. I don't think there is any need. And also you can see A need not be symmetric over here. Okay, just write over here that A need not be necessarily, okay, need not be necessarily symmetric over here. In this case, in the sixth point, the matrix A need not be necessarily symmetric. Okay, so this is also a thing which you will have to remember. Okay, now if A and B are two symmetric matrices, now over here it is necessary that they are symmetric, or in the seventh condition it is necessary that they are symmetric. Then BAB and ABA are also symmetric matrices. Okay, so you try to take the transpose, and when you try to take the transpose, you clearly get that BAB transpose is equal to B transpose A transpose B transpose. Okay, so it is BAB. Okay, A transpose equal to A, B transpose equal to B, so BAB is symmetric. Okay, similarly you can prove for ABA, there is no nothing big in it. Okay, all positive integral power of a symmetric matrix are symmetric. Okay, all positive integral powers, okay, positive integral power of a symmetric matrix are symmetric. Now what does it mean? Positive integral power means plus 1, plus 2, plus 3, plus 4. Okay, so we can call them positive integers. So all positive integral powers of a symmetric matrix are symmetric. Okay, so let us look at the proof of this. Let A be any symmetric matrix of order k. Okay, and n is a positive integer, then clearly your order of A is k and it is symmetric, as it is given that A is symmetric. So symmetric means it must be square matrix. Okay, square matrix means the order will be k cross k. So instead of writing k cross k order, we simply write order k. Okay, now n is a positive integer, so A to the power n, matrix A to the power n will mean like this: A multiplied by A multiplied by A n times. Okay, so when you try to take its transpose, then clearly on both the sides it will be transpose. Okay, and I had already told you that this term will come first, second last term will come here, these two terms will go here, but all are identical. So what will happen? As all are identical equal to A, so A to the power n transpose is equal to A transpose A transpose A transpose A transpose n times. Okay, this has come n times. And when I had already told you that it is a symmetric matrix, so A transpose will be equal to again A, so these terms will be equal to A, again it will be n times. Okay, and as again it will be equal to n times, so it will be equal to A to the power n. Okay, again it will be equal to A to the power n, where n is positive integer, right? Where n is positive integer. Hence all positive integral powers of a symmetric matrix are also symmetric. Okay, hence all positive integral powers of a symmetric matrix are also symmetric. This is very clear from this. Okay, and the alternative proof is over here. Okay, you can have a look at that also, that let n be even. Okay, for even and odd number we are considering two separate cases. Okay, and let n equal to 2k. Okay, now this 2k is different from that to k, the order which I had told you. this k is not equal to order over here. Actually I must have taken some other suffix over here. Let us consider that to be equal to s. Okay, let us consider that to be equal to s. So this is s, this is s, this is s. Okay, and this is 2s plus 1, 2s plus 1. So for even and odd numbers we are proving that your transpose comes out to be equal to the original matrix. So clearly those will also be symmetric. Okay, so it has been proved over here. You need not worry about it. Okay, and don't confuse this k with the k which has been told to you as the order of a. That order of a was different k and this is different k. That's why I took it as s. That's why I took it as s. Okay, so that's the reason why I took it as s. Now the ninth property, if a and b be two symmetric matrices of same order, okay, then ab is symmetric if ab equal to ba, that is if a and b commute. Okay, so clearly you can see that thing over here, that ab transpose equal to b transpose a transpose, which is equal to ba, as a and b are symmetric. So now if this ba, this ba is not equal to ab in case, then ab transpose will never be equal to ab. So ab will not be symmetric until ab equal to ba. Okay, so that's the thing. Okay, so you have to take care of that. So ab is symmetric matrix clearly. Okay, ab is symmetric matrix, but when ba will be equal to ab, clearly we can see when ba equal to ab, only then ab will be symmetric matrix. Okay, so now we will move on towards properties of skew symmetric matrix. Okay, what is the skew symmetric matrix and what are its properties, various properties? We will move on towards that. So skew symmetric matrix, a square matrix A equal to Aij is called skew symmetric matrix. IFF if A transpose equal to minus A. Now I had told you that symmetric matrix, what is symmetric? Symmetric matrix is such a case when A transpose comes out to be equal to A. But if A transpose comes out to be equal to minus A, suppose, then it is what? Skew symmetric matrix, clearly. So in skew symmetric matrix, you are both the side diagonal elements, the elements on both the side of the diagonal, those are going to be your what we can say, suppose I have this 1 2 3 4. Okay, let us for simplicity assume it is 2 cross 2. Okay, so when I try to take its transpose, it will be 1 2 1 2 3 4, right? So this is what is if we want that it should be skew symmetric, then this should be minus 2, this should be 2, and this should be minus 2, this should be 2. And when we try to take it, its minus sign, along with that minus sign, it comes out to be equal to A. Okay, so you can clearly take any example and see over there, and it will be clear from the upcoming discussion also that if A transpose comes out to be equal to A, then it is symmetric, and if A transpose comes out to be equal to minus A, then it is skew symmetric matrix. Okay, so in skew symmetric matrix A12, that is Aij, so 1 2 will be equal to minus of A21. So the off diagonal elements, the elements above and below the principal diagonal, have an exactly opposite sign. Got it? So properties of skew symmetric matrix. If all diagonal elements of a skew symmetric matrix are equal to 0, okay, what are the properties of skew symmetric matrix? All the diagonal elements of a skew symmetric matrix are equal to 0. The diagonal elements of a skew symmetric matrix are equal to 0. You need to remember this thing very well. If the diagonal elements are not 0 now, then this property will not hold. Which property? This property. You only tell me one thing. that suppose I have some skew symmetric matrix of this kind. Okay, suppose I have a matrix of this type, and if I take its transpose will be 1 2 minus 2 3. Its transpose will look like this. If I try to multiply this with minus sign, then clearly these diagonal elements become inverted in sign. But if I put these to be equal to 0, then only these two will be interchanged. Okay, so that's the reason why diagonal elements, principal diagonal elements of a skew symmetric matrix must be equal to 0, so that this condition is satisfied. A transpose equal to minus A condition. For that condition to be satisfied, it is necessary that all the diagonal elements of a skew symmetric matrix are equal to 0. Diagonal elements must be equal to 0. Okay. Now let A be any skew symmetric matrix. Okay, suppose A is any skew symmetric matrix, then clearly Aij equal to minus Abi. Okay, for all I comma j. Okay, for any skew symmetric matrix, I had already told you that elements above and below the principal diagonal on both the sides have signs opposite to each other. Okay, so Aij equal to minus Abi. Okay, so Aii will be equal to minus Aii for all I. How? For all I equal to j. Now for suppose I take a special case, it is saying for all I and j. It is not written that I and j must be distinct. It is not given that I and j must be distinct in this. So if I take I and j to be identical, clearly I and I must be same over here. Then Aii will be equal to minus Aii, and 2 times of Aii equal to 0. So Aii equal to 0. So clearly the diagonal elements have turned out to be equal to 0. What have the diagonal elements turned out to be? Equal to 0. Because what does this Aii denote? It denotes diagonal elements basically. So diagonal elements have turned out to be 0. Hence all the diagonal elements of a skew symmetric matrix are 0. So that is the thing. Hence all the diagonal elements of a skew symmetric matrix have come out to be equal to 0. This is very very clear from this discussion. Okay, let me just see over here that how much we are left with. Okay, so just a second. Yes. So let's move on. Now the second property is, in case of a skew symmetric matrix, all the elements above and below the principal diagonal are equal but opposite in sign. This also I have already told you. Okay, this is your principal diagonal, right? So all the elements above and below, you can clearly see that they have opposite sign. The opposite sign, this is opposite sign, this is opposite sign. There is nothing worth telling that. Okay, and I hope you are making the notes side by side. Okay, I hope you are making the notes side by side. So if you are making the notes side by side, then it will be very much beneficial to you. Every skew symmetric matrix of odd order is singular. Every skew symmetric matrix of odd order, okay, odd order is singular. Well, even order, it is a perfect square. Now I will explain this also. Okay, let A be any skew symmetric matrix of order n. Suppose A is any skew symmetric matrix, its order is n, where n equal to 2k plus 1. Okay, order n, again it will be a square matrix, right? For a matrix to be skew symmetric also, it must be a square matrix. Okay, so order n means it is of the order n cross n. Okay, order n simply means that it is of the order n cross n. So if I say it is of odd order means how is an odd number represented? Odd number is represented as 2k plus 1, and even order will be represented as 2k. Okay, so n equal to 2k plus 1. Now we have to prove this, that determinant of a equal to 0. Why we have to prove determinant of a equal to 0? Because it is given that if the order is odd like this as given here, then the skew symmetric matrix is singular. and singular matrix implies that determinant of it will be equal to 0. So we have to see whether we have to prove whether determinant comes out to be 0 or not. So suppose A is a skew symmetric matrix of order and then A transpose equal to minus A from the previous property, right? A transpose is equal to minus A, and this definition also you have to remember that a matrix will be singular when its determinant comes out to be equal to 0. Okay, a matrix is singular when its determinant comes out to be equal to 0. For a matrix to be singular, its determinant must be equal to 0. So A transpose equal to A, right? And this is the case here also. You can clearly see this, that it is in case of odd order it is singular, okay, and in case of even order, that is n equal to 2k, when the order is even means 2 cross 2, 4 cross 4, okay, and over here we are discussing the case of 3 cross 3, 5 cross 5, 7 cross 7, etc. What is this? This is a case of 3 cross 3 matrix, 5 cross 5 matrix, 7 cross 7 matrix, 9 cross 9 matrix, etc. And when we tell about even order, what is this case? Even order case is clearly equal to it will be a perfect square in that case. That also I will prove. So even order, what is the case? 2 cross 2, 4 cross 4, 6 cross 6, 8 cross 8, like that. Okay, so in that case n will be equal to 2k in the second case, but that I am going to prove later on. First of all, let us look at the proof of odd order one. Okay, first of all let us look at the proof of odd order. So A transpose is equal to your minus A. Clearly you can clearly have a look at this. So so clearly if two matrices are equal, then their determinants must also be equal, right? Their determinants must also be equal. If two matrices are equal, A transpose is equal to minus A, so clearly their determinants must also be equal. So their determinants are same. So determinant of A equal to 1 to the power minus n, determinant of A. How this has come? Clearly from this thing. And how this thing has come? You know this very well, that determinant of A and A transpose are the same, because you know this clearly that for a square matrix, okay, for a square matrix this property holds good for a square matrix, okay, that determinant of A equal to determinant of A transpose for a square matrix, okay, determinants come out to be the same. So clearly you might have learned determinant in lower classes. Over there one property is there, that determinant of A transpose comes out to be equal to determinant of A. So you must have learned that property in your lower classes in 12th standard. So determinant of minus A is equal to minus 1 to the power n determinant of A, okay, minus 1 to the power n has come out in the form of power, okay. So minus 1 to the power n determinant A, okay, and n is equal to clearly n is equal to your 2k plus 1, because n is odd. We had already discussed this. So 2k plus 1, and minus 1 to the power odd is equal to minus 1 to the power odd is equal to minus 1. So minus 1 will come, okay. Minus 1 to the power odd is equal to minus 1, and minus 1 to the power even is equal to 1. You have already learned this. So clearly both these things are eventually your 2 times of this equal to 0, and after you get that, determinant of A is equal to 0. So every skew symmetric matrix of odd order, so determinant has come out to be equal to 0. So every skew symmetric matrix of odd order is clearly singular. Now if the order is even, suppose if the order is even, then what will be the condition? It should be a perfect square. So that's what we are going to prove here, okay. For even order A equal to this thing, and determinant of this A will be equal to, clearly, as it is skew symmetric, so these two will be equal, right? In opposite sign it will be, magnitude will be equal, sign will be opposite, okay? Equal but opposite sign, as A is skew symmetric. So clearly always determinant of A will be clearly 5 into 5, that is 5 square. So clearly you can say if it is A also, then it will be equal to minus A, and minus A, minus of minus into minus A into plus A, that is equal to A square, okay? So instead of taking 5 in the examination, you can take A and minus A, because A is skew symmetric, matrix A is skew symmetric clearly, and as matrix A is skew symmetric, so you know this very well that this will be the case. But still this is not a valid proof. In order to have the proof, we need to look at the second slide, okay? And I have not given you the proof. I don't think it will be asked, okay? I have not given you the proof of this. I don't think it will be asked, but still you can prepare it on your own, okay? So let's have a look over here. Find the determinant of the matrix, this one, okay? Now clearly this is a skew symmetric matrix, you can clearly see this, and 1 2 3 4 5, 1 2 3 4 5, okay? It is a 5 cross 5 matrix, okay? Also, along with being 5 cross 5 matrix, it is also what? It is also a skew symmetric matrix. Because why it is skew symmetric? Because elements on the opposite side of principal diagonal, have opposite sign. Elements on the opposite side of principal diagonal, this is your principal diagonal, and this element minus of this element equal to 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 minus of this minus of this equal to minus of this, and this equal to minus of this. So clearly you can see that it is a skew symmetric matrix, as the corresponding elements on both the sides of the diagonal, have what? Have opposite sign. So as they have opposite sign, so clearly they will be of it will be a skew symmetric matrix, okay? So clearly if we find out the determinant of this, then clearly we can say that the matrix is skew symmetric, matrix of odd order. The matrix is skew symmetric matrix of odd order, okay? So determinant of A will be equal to 0, okay? I had already told you right now that if a matrix is skew symmetric and it is of odd order, why odd order? 1 2 3 4 5, so it is 5 cross 5, right? And it is a square matrix also, and it is 5 cross 5 square matrix, and 5 is an odd number, and it is a skew symmetric matrix. So clearly determinant of A will be directly written as equal to 0 by using that property which we have learnt just moments ago, okay? Now let A be any skew symmetric matrix, then K is also skew symmetric matrix. This you can prove yourself, okay? Your homework. A be any skew symmetric matrix, then K is also skew symmetric. This you can prove clearly. If A and B be two skew symmetric matrices of same order, if they are two skew symmetric matrices of same order, then lambda 1 A is also skew symmetric, that is linear combination is also skew symmetric. This also you can prove, okay, on your own, okay? Still I think, okay, you know, you have to prove it on your own. Now let's look at this, the sixth property. A and B be two symmetric matrices of same order, then AB minus BA is skew symmetric matrix. So let us go into the proof of this. This is something new, okay, new kind of thing. So just go through these three steps. AB minus BA transpose. Okay, if in case it comes out to be equal to minus what I have told you, A transpose equal to minus A is the condition for skew symmetry. Now in place of A, just put AB minus BA everywhere. Okay, in place of A, just put AB minus BA everywhere. So over here AB minus BA will come, and here minus of AB minus BA will come. So after I apply this property, I realize that it is BA minus AB. Okay, so clearly you can see that this is suppose A, so it has come out to be equal to minus A. Okay, by using the properties which we have learnt just now. Okay, so it is AB minus BA is your skew symmetric matrix clearly, and all these small things which I am teaching, these are of great use. Okay, now seventh property, if A and B are two skew symmetric matrices, then AB is skew symmetric if AB equal to minus BA, A and B anti-commute are anti-commutative. Okay, or we can say they anti-commute with each other. Okay, so this property you can see the proof of it. Okay, very easy proofs. I don't think there is any need to tell even. Okay, you can note it down and understand yourself. Okay, just note it down. I am taking a break for 30 seconds. Okay, just note it down. I don't think there is any need to even explain it. Okay, because A and B are skew symmetric, so these conditions will hold, and minus into minus will become plus. Then if we want to prove that AB transpose equal to minus AB, so if they are not anti-commutative, then this can't hold, then. Okay, so they must be anti-commutative, right? Got it? So AB is a skew symmetric matrix. Okay, then eighth property is ABN is square matrix. A minus A transpose is skew symmetric matrix. You can prove it. There is no need to prove. How will you prove it? Just take its transpose. Just take it transpose. What means A minus A transpose. Okay, just write like this: A minus A transpose. Okay, which in turn will equal to A transpose minus A transpose. Okay, so it will come out to be A transpose minus A. Okay, so then you can write it minus of A minus A transpose. Okay, so clearly you have got transpose equal to minus A transpose equal to minus A form kind of equation of A transpose equal to minus A form you will get, and so you can prove the property number 8 also very easily. Okay, so all positive even integral powers of a skew symmetric matrix is symmetric. Okay, all positive even, just see, all positive even integral powers. Okay, positive and even integral. Okay, even means 2, 4, 8, etc. Okay, all positive even integral powers of a skew symmetric matrix is symmetric, whereas all positive odd integral power is skew symmetric. Okay, so let us look at the proof of this. Let A be n is skew symmetric matrix of order n. Order n means it will be n cross n matrix, and it is skew symmetric also. So the elements on the opposite side of principal diagonal will have opposite signs, right? It is of order n, so it will be it will be clearly n cross n. Then order is n, and you want to say that for even order the condition is we are taking powers, basically powers. So power is equal to k, suppose. Okay, so let us see over here. suppose the power be m be odd positive integer, then a to the power m transpose a m times, and its transpose will be taken, then a transpose a transpose a transpose a transpose, this is m times clearly. Okay, we are assuming m to be the power, and never confuse between power, and your order. Okay, it is n cross n order matrix, okay, but we are taking the power. Okay, we are taking power, a to the power m is odd positive integer, so a to the power m transpose, okay, a into a m times, okay, and its transpose is taken, so a transpose m times, okay, and when transpose of a is taken, so a transpose comes out to be equal to minus a, okay, a transpose comes out to be equal to minus a, so all these things will eventually turn to minus a, which is m times. Okay, so clearly you can see this thing, that if m is odd, okay, if m is odd, then minus 1 to the power m a, like this the term is there. Okay, minus 1 to the power m a, like this the term is there. Now if m is odd, then minus a will come. Okay, minus a to the power m will come. Okay, and if m is even, then minus 1 to the power m will become 1, and a to the power m will come. Got it? So that's what has been discussed, that this is the case when m is odd. When is this case? M is odd. Okay, so it is skew symmetric matrix when m is odd. Okay, and hence all positive odd integral power of a skew symmetric matrix, okay, is a skew symmetric matrix. Okay, now you can prove it for even power also. I have already told you the same proof will be there. For even power also the same proof is going to be there. For even order also the same proof will be there. Instead of this, you will get, instead of this minus sign, what is this? This is basically your minus 1 to the power m, a to the power m is there. Okay, what is there? Let me tell you. Okay, let me tell you, minus 1 to the power m, a to the power m is there. Okay, and eventually if this m is your odd, then this minus a to the power m will remain. But if m is even, then my a to the power m will come, because minus 1 to the power m will become 1 plus 1 for m is even. For m equal to even number, minus 1 to the power m will become 1 plus 1. Okay, and for m odd, minus 1 to the power m will become minus 1. So these are the two cases. So a to the power m transpose equal to minus a to the power m. Okay, for m to be odd. And if m is even, okay, if m is even, the proof is not given. Okay, then that condition will hold which has been written. Okay, for positive even integral powers of a skew symmetric matrix is symmetric. Okay, positive even integral powers, it will be symmetric, and positive odd integral power, it will be skew symmetric. So you can clearly verify all these things on your own. You can clearly verify this. Okay, then again one last thing which has been written without any proof. Okay, is that if a and b are two skew symmetric matrices of same order, BAB are also skew symmetric. This is very easy, very easy. BAB transpose you will take. Okay, then it will come to be B transpose, A transpose, B transpose. Then you know this very well, that B transpose equal to minus B, because A and B are skew symmetric. A transpose equal to minus A, B transpose equal to minus B. So one minus sign will remain, minus B, A, B will come. Okay, then it is clearly skew symmetric. So you can easily solve this 10th property. Okay, it is of no use to discuss it in detail over here. Okay, so that's all about the third lecture of maths optional. Good night, Shubh Ratri, Shab Bakhair. Thank you very much. Jai Hind, Jai